Good morning for Indian friends and good afternoon for Australian friends and good night for our USA experts.
गुड नाइट आप कहेंगे तो हम जाके सो जाएंगे.
वक्रतुंड महाकाय सूर्यकोटि समप्रभा निर्विघ्नं कुरु मे देव.
भाई साहब की यहाँ तो 11:30 बज रही है.
सर्वकार्येषु सर्वदा. इसलिए सब लोगों को गणपति का याद करके हमारा FDP प्रोग्राम we wanted to start. So now I request Prasad, Dr. Prasad to play the university song, please.
Okay.
जय हो नवयुग निधि की जय हो, जय हो नवयुग निधि की जय हो. पावन हिमगिरि के चरणों में शीश झुकाए विशद तराए. शस्य श्यामला तरु दृढ़ वसना सहज उर्वरा धरणी सुहाई. उसके हृदय कमल में विकसित हरित स्वर्ण छवि सौरभमय हो. जय हो नवयुग निधि की जय हो. अन्य यंत्र गो पुस्तक ब्रह्मंड कृषि अभियंत्र विश्वविद्यालय. अपना प्रण है ग्राम अभ्युदय. देश प्रगति विज्ञान विभाग. संज्ञशील स्वाध्याय साधना से समृद्ध भारत निर्भय हो. जय हो नवयुग निधि की जय हो. जय हो, जय हो, जय हो.
Thank you, Professor Shiva Prasad. Myself, Jyothi Prasad, Professor in Civil Engineering Department, co-coordinator of ATAL FDP program. Welcome you all for this inaugural function. Professor Vijay Singh, a distinguished professor from Texas A&M of USA, he has accepted our invitation for team address. Even though it is a midnight for him, still he is so excited to address on this occasion. I welcome you, sir, from India and our College of Technology. Welcome you, sir. And our Professor Gajendra Singh, he was also a former Vice Chancellor of the Doom University, and now he is also in USA. And he is also accepted our invitation to be a guest of honor and to address, bless us during on this occasion. And welcome you also, sir. And it is also we are also lucky to have two persons who has got the Lifetime Achievement Award of the university, Professor VP Singh sir and Gajendra Singh sir. Both of you, welcome you, sir, for this inaugural function. And we also have Professor Basant Maheshwari from Western Sydney University. He is also a source of inspiration. By seeing him, we also feel motivated to work. He is a key person of Australia-India Water Center. Welcome you, sir, for accepting to being a guest of honor on this function. Extend my hearty welcome to our Professor Dr. Alkananda Ashok. She is a Dean College of Technology and she is also a key person for motivation of all such activities and she is behind us. So that's why we can able to succeed. So otherwise it would not be possible. Welcome, madam. Even though आपका काम था, फिर भी आपने join कर लिया. Then we extend my hearty welcome to all the deans and head of the department, Professor Dr. P.S. Mahar, and all the faculty members of the university and the officers of the university, and extend my welcome to all the participants who has joined well in time, before the time, for attending this inaugural function. Once again, I welcome you all for this inaugural function for starting of the FDP program. Thank you. Now I request Professor H J Shiva Prasad, who is the coordinator of the FDP program. Professor Shiva Prasad, please. हेलो हेलो हाँ मैडम प्रोग्राम कितना बजे से है अभी 9 बजे से स्टार्ट
just a moment. Yeah, good morning to all of you. This entire ATAL Academy program. Note that this program is ATAL Training and Learning Academy sponsored 5 days FDP program on urban hydrology is sponsored by All India Council for Technical Education, New Delhi, under the broad name of ATAL. So note that this program, as you are aware, it runs for 5 days, and you know all the experts. Professor Jyothi Prasad, she has already introduced about inaugural session experts that includes Dr. Alakananda Ashok, Professor Basant Maheshwari ji, Professor Gajendra Singh, and distinguished Professor VP Singh, including other experts, those who are on the background. Maybe Dr. Sharad Jain has joined, that's what I could see, and many others have joined in addition to them. So note that this program runs for around 5 days. There's various experts, and this is the inaugural session. It runs for an hour or so, and Professor Vijay P. Singh, he will be talking on the theme address, that is urban hydrology. So you might have seen during the last few decades, there will be a lot of urban floods, particularly Bangalore floods, Chennai floods, then Jammu floods, even in Delhi also, you people all are observing during the recent monsoon. So note that we thought that it is a good opportunity to start this program, and we have put up a proposal to AICTE, and immediately they accepted to organize this program virtually. So even though we could not organize this one at Pantnagar itself, definitely next time after this COVID situation, we will organize at Pantnagar itself this program. So note that these programs will be running for 5 days, and you can just see the galaxy of experts, including Professor Vijay P. Singh from Texas, and Dr. Sharad Jain. He was earlier director of National Institute of Hydrology, Roorkee, and presently distinguished visiting professor at IIT Roorkee, a well-known IIT Roorkee, and Professor Mazumdar, who has actually worked on Bangalore floods. He is from Indian Institute of Science, Bangalore, and he is an, I should say, is an person behind that all the recent studies automation which is taking place both at Chennai and also Bangalore. Professor Mazumdar will be there, and Professor Mohan Kumar, another stalwart from Indian Institute of Science itself. Professor Mohan Kumar will be there. Both are from Indian Institute of Science, Bangalore. And then from our own Uttarakhand, Dr. N.K. Goyal, Narendra Kumar Goyal, he is from IIT Roorkee. He is also Bharat Singh Chair Professor and also Senior Professor from Department of Hydrology. He will be there from IIT Roorkee. In addition to that, another young guy, Dr. Kuri, presently they are working on IIT Madras flood project, and automation also involved. In that project, Professor Puri is working, and he will be joining us. Then Dr. Jagadish from ISRO, okay, who has worked on floods. He has urban floods particularly, or urban hydrology in specific. He will also be joining. And Professor Guru or Munuvalli, he did his PhD from IISc Bangalore and presently a senior professor at Maharashtra. And Dr. Danya, he is working on climate change and other aspects which its affects at. She is working on a project at IIT Delhi as of now, and she is associate professor over there, and she will be sharing her experiences for 2 sessions also. Then Dr. Meenu Ramadas, she is from IIT Bhubaneswar. Okay? So she has also worked earlier at IISc Bangalore, and now she is an faculty at IIT Bhubaneswar. She will also be joining for this program. Then, of course, there is a Karnataka State Disaster Management Center is there, who are the implementing agencies along with in association with IISc and Dr. Shubha Avinash, who have worked in the field. They are be present over there. And of course, there is one talk, motivational talk by Asha Kiran. She is a senior deputy general manager at Kudremukh Iron Ore Limited from Bengaluru. She will be talking on motivational aspects, because in ATAL Academy specifies one expert lecture should be there on personality development, or motivational lecture has to be there. So that will be taken by Asha Kiran. She is from Bengaluru, and she is the senior deputy general manager at Kudremukh Iron Ore Limited. And of course, Dr. Jyothi Prasad, she will be speaking on QGIS applications for the use of urban hydrology. So that she will be speaking. So here is a brief highlights of that FDP program. Note that there will be 3 sessions daily, and each of totally 2 hours. 1.5 hours will be expert lecture and half an hour for interaction. So this is what we kept it. Anyway, this has been shared with all the participants, including experts also. I will not go to details of this one because of shortage of time. Anyway, there will be 3 sessions for all the 5 days. Okay? So 9 to 4:30, all the participants will be busy in this program. And note that coming to the participants, they are the stakeholders of this training program. There will be 22 states are represented in this program, and around 150 participants are participating in the virtual faculty development program. So note that major chunk of participants are from Uttarakhand, of course, then Gujarat, then Karnataka. So these are the 3 major states where large number of participation, around 20 each. Then comes Tamil Nadu, and of course other many other states throughout India. They are involved. They are presented. Their participation is assured in this FDP program of 5 days. So note that there will be a good representation of female participants also. More than 40% of the participants are female, and approximately around 60% are male from different parts of the country. And note that today we shall start with Professor Vijay P. Singh. He is from Texas A&M University. He is also a distinguished alumni of this university, and he has received a lifetime achievement award from this university. And he is starting that first session, particularly on urban hydrology, problems, challenges, and opportunities. And of course, next session is followed by Professor Mazumdar from IISc Bangalore. Then next session by Karnataka State Disaster Management Center, Shubha Avinash. So this is all overall about the program. And lastly, I thank the AICTE, All India Council for Technical Education, for sponsoring, for accepting our proposal, and through ATAL Academy, thanks to them, and thanks to our own university, including Professor Alkananda Ashok, College of Technology, for providing all the facilities and also for successful organization of this program within a shorter time, and that too during this COVID period. So lastly, I am also thankful to our Australia India Water Center who are supported academically in this program. So finally, thanks to all. Thanks to all the participants, and once again I welcome you all for this academic program, FDP program sponsored by AICTE. Thanks. Welcome to all the participants again. Please.
Thank you, Professor Shiva Prasad, for briefing about the course and experts, as well as the course about the program. Now I request our head of the department, Professor P.S. Mahar, to brief about the department, please. Dr. Mahar.
Thank you, Dr. Jyothi Prasad. Professor Vijay Singh, Professor Gajendra Singh, Professor Basant Maheshwari, Professor Alaknanda Ashok, the distinguished visitors, speakers, and guest of honors, and Dean Technology respectively. The faculty members of different departments of the College of Technology and heads of departments of the College of Technology as well as other colleges of the university, and dear participants, many of whom are faculty members in different colleges of the country, and many of them are budding big experts of the country, that is, they are pursuing their PhD program. On behalf of myself and faculty members of the Civil Engineering Department, staff and students of Civil Engineering Department of College of Technology, I welcome you all. For those who had never been to this beautiful campus at the foothills of mighty Himalayas, it is my request, please try to visit sometime later on. You will really get a lifetime experience in visiting this beautiful campus, which is a campus town, basically. My job here as head of the department in this inaugural session is to introduce the Civil Engineering Department. Our department came into existence in 1962. Then we started MTech programs in 1969 and 1970 and 1985 respectively in structural engineering, hydraulics and water resources engineering, and soil mechanics and foundation engineering. Recently, later on in 2012, we have started PhD program in civil engineering. We have 13 staff members present out of total 19 section strength. Out of 13, we are 5 professors, 1 associate professor, and remaining assistant professors. The plus point with our faculty is that all of us are having PhD degree, except one gentleman who is about to submit PhD degree in Hydrology. So that is strength of our department, and the best part of our department has always been the good bachelor's education. We have very good education at bachelor's level. As a result, our students in the past has scored all India rank number 1 in GATE examination 2 times, and up to 10th rank, up to 50th rank, up to 100th rank, sometimes second, third, many times. So that is our plus point. Another positive point with our department is that we are a revenue generating department in the college as well as university. In the last 10 years, we have generated revenue to the tune of 50 lakh to 1 crore rupees annually. So these are two plus points about our department. I hope the participants will get a very good introduction as well as in-depth knowledge of the topics on urban hydrology and the consequent design principles for release of this inconvenience to the citizens. And especially as Professor Prasad introduced here, the speakers, some of them are known to me personally, and some of them I know through their publications. Professor Mohan Kumar, and from down south, Professor Sarajan and Professor N.K. Goyal from Roorkee, and many more. Many of them I do not know personally. They are gentlemen, ladies and gentlemen, I would say that they are perhaps the best experts on the field of urban hydrology within the country. Above all, the almost one of the best experts in the field, Professor Vijay Singh, is there to give you some basic tips. Hope you will, at the end of this program of this FDP, you will certainly go to your colleges, to your towns with some good tips in the subject. Especially, please, I would request you all to please listen attentively. Please attend the all talks sincerely and attentively, because many of them are working for the last 1 decade or more on the topic of climate change. And climate change not as a science subject, but the effect of climate change on urban planning and town planning. So please, it is my request that utilize this opportunity. This is almost lifetime opportunity that such experts have been gathered at a place, probably because of this COVID effect. With, I thank you all for attending this program organized by our department, and I wish a grand success to the organizers and to the participants. Thank you very much.
Thank you, Professor Dr. P.S. Mahar, for briefing about the department. So now I request our Dean College of Technology, Professor Dr. Alaknanda Ashok, to address on this occasion, please, madam.
Namaskar. I'm really delighted that College of Technology, who is the faculty of GB Pant University of Agriculture and Technology, is organizing this 5 days FDP program. On behalf of College of Technology, welcome all the participants, our eminent speakers and our faculty members who all are participating in this FDP program. As Dr. Jyothi, Dr. Prasad and department, Dr. Meher has already briefed you about this FDP program. I will be brief, but I would like to say that Dr. Gajendra Singh and Dr. Vijay Singh, they all are always with us. And like we can see, it's around 11:30 and they are so attentive and attending this program and ready to address all of us. I really appreciate your efforts. And similarly, I am not the expert of hydrology, but I have been attending many sessions with Dr. Vasant Maheshwari, and he is an expert in hydrology. I have get to know about so many things, and I am really privileged to have such knowledge uh, uh, received from Dr. Maheshwari. I welcome all of you on behalf of College of Technology, and I would like to tell you in very brief about the College of Technology. The College of Technology, one of the 7 faculties which are running in GBPUAT University. We have 8 branches, and the best feature of our engineering college is that we have agriculture engineering as well as different engineering branches, basic engineering branches like electrical, electronics, computers, mechanical, civil, and industrial production, IT. So we are running with all these branches. So what I feel personally, being the dean of this College of Technology, that we can have good developments with interdisciplinary combinations. Like today's session is on urban hydrology, and I feel this is the need of hour. And as Dr. Prasad told us, I must congratulate the effort of our coordinator, because he has he has bring the most expert person, IITs, ISC, ISRO, who have expertise in hydrology. I must congratulate the efforts of Dr. Prasad. And I feel I shouldn't take much time, and we are eager to listen Dr. Vijay. So I welcome again on behalf of College of Technology, and I feel this session, this FDP program will be a very fruitful program, and during the discussions, we can have some good solutions regarding the climate change, floods, which are. So my heart is welcome, and I congratulate our coordinator, efforts of Civil Engineering Department, support of our head of the department, Dr. Meher, to organize this FDP program. Thank you so much to our alumni, Dr. Gajendra Singh, Mr. Gajendra Singh, and Dr. Professor Vijay Singh. Thank you so much for joining. Namaskar.
Thank you, madam, for your encouraging talk, and it is also sort of motivation for us to conduct this type of activity. And even one of the expertise, Asha Kiran, she is Deputy General Manager. She is also joined in this program, inaugural function. Asha?
Yeah, good morning.
Good morning, and welcome you also for the inaugural function.
Thank you so much. Thank you so much.
Thank you.
Yeah.
So now I request Professor Vasant Maheshwari. He is from Western Sydney University, Australia, and he is the starter from the GAN program, and many more activities he has made of MOU in our university. Along with that, he is a key person to link with the Australia-India Water Center and many more future works. And please welcome our Professor Vasant Maheshwari for blessing on this occasion, please.
Thank
Dr.
you.
Dr. Vasant start, I must say one thing, like COVID is troubling all of us, but we are having blessings in disguise that the participants from US, from Australia, and all over the world, they are connected with us. I am like, we can say thank you to COVID for this one thing.
That is very true. Thank you. And first of all, thank you to Professor Shiva Prasad ji and Jyothi ji to invite me and to be part of this. And I have been to Pantnagar 2 times now, and it is a beautiful campus, and really enjoyed, and I have good memories. And also 2 people I admire so much, Professor Gajendra Singh ji and Professor VP Singh Saab, who had starting career from there. And so it is great to see both of them here. And they have been my great mentors and teachers, and nice to see them. I also want to acknowledge Dr. Alaknanda Ashokji and Dr. Maher, who is the Civil Engineering Department head, and all the distinguished experts and participants. And we have started this journey of collaboration. And I think probably VP Singh Saab suggested to Shiv Prasad ji about this Gyan program where it all started. And now we have this MOU, and then Australia-India Water Center, Young Water Professionals Training Program going to start soon, and so on. So it has been a great thing. And so I think the topic of urban hydrology is very important, especially a lot of urbanization happening all over India and all over the world. And what it means is we are converting very productive agricultural land into urban areas. And now we have reached more than half of the population of the world is in urban areas. And what urbanization does is the change in land use. And change in land use means we are removing vegetation and the hydrology gets changed. And then it affects peri-urban areas and rural areas. So water is very important and urban hydrology is very important. And you have the right people to really give you some deep insights into what it means. While I'm here, I would like to share some highlights about the collaboration we have developed now. It's called Australia-India Water Center. So I will try to share some slides too very quickly. So the Australia-India Water Center was inaugurated late last year. And the idea of the center is to develop opportunities and create synergy towards water research, education, water research and education between India and Australia, with special focus on water and food security research. Also, our aim is to develop a joint master's level program in water futures, and again, very much online. So it's a flipped classroom type based on number of short courses, making up the subjects and so on. And also develop programs of student staff exchange, workshops, conferences, short-term training programs in water sector to government agencies and participants. And we have 15 partners from India, plus Department of Water Resources, Government of Maharashtra, and 7 universities from Australia and the South Australian Department of Environment and Water. And these are some of the photos from the inauguration. So the Jal Shakti Minister Gajendra Singh ji and the Federal Education Minister from Australia, the Karnataka Water Minister, the High Commissioner of India to Australia, and High Commissioner from Australia to India. They were all present, and it was really a good sort of launch. Then it led to good sort of publicity, and it has been really going from I just want to so this has been really good initiative between India and Australia, and bringing a lot of collaboration, networking, and connecting with the different people. And so this is, for example, we have been given opportunity to run young water professionals from India training program. we are developing some master's program, short courses, and so on. And this is one of the collaboration we are working on through GB Pant University. So thank you very much, and I really wish all the success in this important training event. Thank you.
Thank you very much, sir, for your blessings and brief introduction of AIWC works. Thank you very much, and for being with us. Now I request Dr. Gajendra Singh, sir, and he is a former Vice Chancellor of the Doon University. And I told he is also a Lifetime Achievement Award of the university. He is also one of the person. So please welcome our Dr. Gajendra Singh, sir, for blessings, please.
Thank you, Jyothi. Dean Alaknanda, Professor Vijay Singh, Professor Maheshwari, Dr. Meher, Dr. Shiva Prasad, and I think all the distinguished people who are going to participate in conducting this course, and especially the participants who are attending this course for their faculty development. Honestly, this is not my area of work, but from common sense, I can say that the urbanization really is changing the whole scenario so much that the sustainability of our natural resources systems is really under big stress. So as the urbanization increases, you see that there's so much of the land which is under agriculture or grasslands and other things get converted into urban settlements, and then it changes the complete infrastructure and all that. So then when you have a rain, the hydrology, whole thing is very, very different. So now you have storm, you have such a big runoff. So previously, most of this water in agricultural lands and grasslands and all those areas used to get absorbed, okay, and infiltrated in the soil and join our groundwater for future use. But in these urban settings, the runoff really, because of the surface is all concrete and all that, and so we are not really using that water in that layer. So, but on the other hand, the consumption of water in these areas is so high because of such a density of population. So the resource which was meant for local, and there was a balance, that all has changed because you are using much more than what you are there. And also there is very little attention paid to harvesting this rainwater. In spite of all the efforts of governments and education, including Pantnagar, I visit and I ask for how many places we have the groundwater recharge. I think the Pantnagar professors can tell how many places they are really water harvesting structures are there. Okay, so I find it that this is the biggest challenge. You have the water use, the demand has gone up so much because of the concentration of populations in the cities, and and whatever we are getting there, we are not retaining it, we are not harvesting it, we are not storing it, we are not saving it. So, and the other thing is the same way. So the water is becoming a big challenge to meet the needs of urban areas. On the other hand, what we are doing is whatever we have, we are actually polluting it. So there is a big problem of water pollution. And so we are producing a lot of wastewater from urban areas, and how to improve the quality of this water so we can reuse it. Can we recycle? Very little is recycled because it's very expensive. And then even to use it for irrigation, there are a lot of challenges because in many cases, it's not really directly usable even for agriculture purposes. So what I will say that because of this loss of natural land cover, changes to that, we are finding that the groundwater is really, we are using or over pumping everywhere, especially in urban areas. In many cities are facing a problem of sinkage. There is I was in Bangkok and we used to always see that it was going down almost 10 centimeters a year or so. And then flood problem became very severe because whatever little elevation we had for the discharge of this water to the ocean, we were losing even that elevation difference. So, and the climate change also has made it worse. The intensity of rainfall has gone up in many, many areas. And this year especially, you have seen that so many places got flooded, very, very severe floods because of this climate change, rainfall intensity. You people are all experts in that. So I think this area, the problems are very big, and it is very difficult to forecast exactly what we are going to expect. And the damage is done in a very short period of time by these situations. So I hope our young faculty, which you are training under this program, will be equipped with all these latest techniques and awareness. And I think we must also somehow get into the policy issues somewhere, that how to educate these our policy makers so we can take due actions to correct this situation. I think these words I'm going to stop, and I wish all the best and very useful and successful program. Thank you very much.
Thank you, sir, for your blessings, and also you joined us in the midnight. Thank you very much, sir, and I welcome once again for this inaugural function. Now it is the time
Dr. Jyothi,
for...
Dr.
Yes,
Jyothi, I would like to add one thing, like Dr.
Some connectivity, madam. Hello.
मैडम आपका माइक
connectivity problem.
And how to increase the water table. If we can have some solutions, then we can suggest further. So we can have a blueprint and we can have fruitful discussions on these points.
Okay.
This is a very nice idea.
Yeah, madam. Definitely, madam. Definitely we can have.
Dr. Gajendra is always a motivating force behind us, because whenever he talks, he gives some good suggestions. Yes. So we must listen him very carefully, and we must store all these things. Very thank you so much, sir, for addressing us and giving us this idea that we should have some discussion, and if we can find some solutions, that will be wonderful in this FDP program. Thank you so much.
Thank you, madam. Thank you. Thank you, madam. So, it is a time for our Professor VP Singh, sir, and he's already, it is getting late still. Just to have a brief biodata, because his biodata is very vast. It may take, I don't know, if you read, it is already the links I have given, but if you start for reading, it may not, it is not enough to study on one day. So that's why I am giving only one very small brief biodata of our Professor VP Singh, sir. And he is a distinguished professor, and he is a regent professor, and Caroline and William N. distinguished chair in water engineering at Texas A&M University, USA. And he is a registered professional engineer and hydrologist, and an honorary diplomat of AICTE and WRE. He is also a distinguished member of American Society for Civil Engineers and honorary member of IWRA, and distinguished fellow of AGGS and honorary member of AWRA. He is a fellow of many societies, And he published extensively in the area of hydrology, irrigation engineering, hydraulics, groundwater, water quality, and water resources. And he is having more than 1,360 journal articles and 31 textbooks, 80 edited reference books, 115 book chapters, 315 conferences papers, and he has received more than 100 national and international awards. And he is having, including 3 honorary doctorates, and he is a member of 12 international science and engineering academics, and he is also a president, served as a president of American Institute of Hydrology and chair of Watershed Council of American Society of Civil Engineering and president of American Academy of Water Resource Engineers, and is president of International Association of Water, Environment, Energy and Society. He has serves of an editor-in-chief of 3 journals and 2 book series, and serves as an editorial board more than 25 journals and 3 book series. And his Google Scholar citation, do we expect how much? Huh? Whether it is 10, is of multiple of thousands, like 70,658. And his H index is 117. So it is not possible for me to read within a 5 minutes. He is having a very vast biodata. So now I welcome Professor VP Singh, sir, to address the theme lecture on urban hydrology, problem, challenges, and its opportunity. Please, sir. Now it is a time for you, sir.
Okay. Okay. Thank you, Jyothi. Can you hear me?
Yes, sir. Yes, sir.
Okay. Okay. Thank you, Jyothi, for a very graceful introduction. Dean Alaknanda Ashoka, Professor Gajendra Singh, Professor Basant Maheshwari, Professor P.S. Mahar, Professor Hari Prasad, and of course, Professor Jyothi Prasad, distinguished workshop participants and speakers. It's an honor and privilege for me to have been invited to speak at the inaugural function of this 5-day workshop on urban hydrology. When Jyothi approached me several months ago to mark on my calendar for sparing the time to speak on this occasion. Of course, being a friend, it is hard to say no, but in any event, she gave me a wide choice of speaking on any technical subject. I thought about it, and I thought in order to have a useful discussion during the succeeding 5 days, it will be important to set the context. And because after all, it's an inaugural function, so rather than talking about differential equations and probability theory and so on, it will be important to sit back and reflect on what essentially the key issues and the key problems in urban hydrology are, and what the key challenges are facing us, and of course what the opportunities arising from these challenges might. And Jyothi, can you please put the slides? I would have preferred to have the slide presentation in my hands so I can do the slides back and forth with a lot more facility. To move to the next one. So let's have a discussion, and I would also like to point out, should anybody have any questions at any time during my presentation, please feel free to raise your hand, interrupt me, and I will be more than happy to discuss. So let's consider this more as a discussion forum rather than a formal speech. So with that, Jyothi, go ahead and put the first slide. I don't see the slide yet.
Now,
Okay, yeah. Okay, so as I said, here discuss what the problems are, what the challenges are, and what opportunities. Can I, if you allow me to share, then I can move the slides. Go to the next slide. Can you hear me?
yeah. Yes, sir.
Yeah, go to
Is
the
it
next
changing?
slide. Can you? Yeah, yeah, can you? No. Yep.
Is it visible?
No, I don't see the slides. I see you. Maybe should we go back and then, okay, let me see. Okay, go back. Let me see if I can. No, there is no slide. I cannot.
Is it visible, sir?
It is visible. Actually, it is. Yeah, it is visible. But can you put the slides on the full screen?
Yeah, it's a full screen only.
No, it's not a full screen. It's a very short screen. It is, the whole screen is divided into 3 parts. On the left part is a sequence of slides, and in the middle part is a very short. Otherwise, you know, let's go over and then perhaps we can have the way we were doing before without seeing the participants.
Okay. How about
Again,
now?
it's the same. Yeah, now it is a little bit better. Yes. Okay, go to the next slide. So these are the 3 problems, as we said. Okay, yeah, go to the next one.
Is it changing?
No,
Is
go
it
to the
changing?
next slide. Yeah, it is changing, but go to the next one. You are going backward. Okay.
This one.
No, you are going back. Okay, yeah, can you put it on the full screen? Yes. Okay, yeah, keep the slides on the full screen. Okay, so let's first discuss what the grand problems are. The grand problem is life's security, which depends upon fundamentally on water security, food security, energy security, environmental security, health security, and ecological security. So in other words, the securities of water, food, energy, environment, ecology, and health are the ones that will ensure life's security. This is the grand challenge that we are facing these days. So go to the next slide.
Is that changed?
So, in order to ensure life security, as I said, fundamentally, we have to ensure the environmental sustainability. We have to ensure the environment, and then we have to sustain in the long term. But this in areas, sustainability of our way of life and the sustainability of our society, or for that matter, human civilization. But this sustainability is constrained by population rise, demographic changes, climate change, land use change, and of course, urbanization, which is taking place at a very rapid pace, rising standard of living, rising human expectations, rising energy demand, and rising food demand. These are the constraints which are threatening environmental sustainability, which in turn is threatening life security. So the grand problems, no, but you are going backward, go forward. Okay. Now, of course, those, the environmental sustainability cannot be ensured without economic development. So the primary drivers of economic development are education, communication, transportation, industry, agriculture, health services, governance, social fabric, cultural, religious, and institutional as well as legal framework. And then, of course, environment, energy, and water. Next one. These are the primary drivers of economic development. Yeah, go ahead. So then, go ahead. So the primary then urban issues are recurring problems which are faced by urban areas are regular and inadequate water supply, inadequate electricity supply, frequent flooding, inadequate transportation systems, unacceptably high pollution, and of course, recurring encroachment into government land. These are the problems that are being faced by urban areas. The next one. So the question arises, what are the causes of these recurring problems? The causes are urban sprawling, growing population, rising demand for water and electricity, inadequate drainage infrastructure, inadequate transportation systems, inadequate garbage disposal facilities, lack of sanitation, disappearance of lakes and wetlands, diminishing parks and forest areas, and recurring encroachment into government lands. So these are essentially the causes which are giving rise to the urban issues or urban problems that I just enumerated. The next one. And then, of course, to continue the causes, then of course the lack of urban planning, lack of urban zoning, climate change, lack of synergy between science, technology, policies, politics, and people. And of course, lack of overall long-term vision. These are essentially the very key issues which are causing the problems that urban areas and for that matter, metropolitan areas are facing these days. Unless we address the issues at the grassroots level, there is no way that we can address those problems. We can solve and overcome those problems. The next one. So the question then arises, so where does urban hydrology factor in? Because after all, the workshop is on urban hydrology. So what is the role of urban hydrology in urban development and in turn in addressing these urban problems? So first, let's see, where does urban hydrology play a part? It plays a fundamental role in urban water supply, water harvesting, urban zoning, urban drainage systems, designing transportation systems, pollution abatement, assessment of climate change impacts, parks and recreational areas and their development, wetlands and lakes, and for that matter, in the entire urban ecosystems. And some of these issues were raised by Professor Gajendra Singh. Yeah, next one. So the question arises, now we know how important urban hydrology is in addressing those problems. So the question is, what exactly is urban hydrology? So the next one. I think we should have a clear concept of what hydrology is, and then of course we'll define what urban hydrology. So in order to capture the essence of hydrology, I think let's first understand the anatomy of hydrology, just like we understand the anatomy of human body. So if we anatomize hydrology, then I think we will have a much clearer concept of hydrology. So there are 6 aspects or 6 components of hydrologic anatomy. First, because it deals with water. So first component is water. The second one is the phase of water. The third one is place of its occurrence. The fourth is the domain of its occurrence. And the fifth one is a scale. And the sixth one is the processes. So the first phase is water. So which means it deals with both quantity as well as quality. So then the next question is, the water appears in different phases. Normally in hydrology, you will only hear about 3 phases. And these phases are liquid, vapor, or solid, means snow and ice. But there's another phase which is called 4th phase. So the question there is, where does water occur? It occurs over land surface, in the unsaturated zone below the land surface, and then of course in the saturated zone below the unsaturated zone. So what is the scope or what is the domain within which water occurs? The domain is described by 3 domains: space, time, and frequency. Then that gives immediately rise to the scale problem, because water occurs at different scales. The scales are divided primarily for the consideration of urban hydrology into 4 scales. That is micro, meso, macro, and mega. So then the question is, what are the processes that are associated with water? The processes primarily are: water occurs, that means occurrence, distribution, movement, and storage. The next one. So these are essentially these 6 components anatomize or describe the anatomy of hydrology. So let's look at little in more specific details the processes of water. The first one is storage. We all know the water storage occurs above, on, and below the land surface. So it occurs above, means what it occurs in the form of water vapor in the atmosphere. So atmospheric water storage is there. Then of course interception storage, depression detention storage, channel storage, storage in lagoons, lakes, reservoirs, storage in wetlands, and then of course storage in the form of snow, ice, and glaciers. So all these essentially pretty much encompass all possible sources of water storage. Then of course water occurs as a flow because it moves, but the movement occurs above, on, and below the surface. So on and above the land surface, that is, water is moving vertically downward, vertically upward, as well as laterally. So moving, that is downward in the form of precipitation, upward in the form of evaporation, as well as transpiration, and of course downward as through flow. But water also moves horizontally as overland flow, channel flow, snow, and glacial movement. And then of course below the land surface, unsaturated flow as infiltration, percolation, and interflow, and of course a saturated flow, base flow, and groundwater flow. So these are essentially the flow processes through which the water occurs. The next one. Then of course, we also, all these are then associated with what we call as hydrologic cycle, because these different phases and different processes are associated in different spheres. And these spheres are connected. So there are connections through the hydrologic cycle amongst atmosphere, land surface, pedosphere, lithosphere, and hydrosphere. But these connections depends because these different processes vary depending upon the scale. So at the large scale, the processes are primarily precipitation, evapotranspiration, and steam flow. The next one. So having said this, having pretty much described the anatomy, now we can say that urban hydrology can be defined as the science that deals with the space, time, and frequency of the occurrence, distribution, storage, and movement of the quantity and quality of water on the surface and below the urban land surface. Or in very simple terms, in a somewhat very subjective and not specific terms, one can say that urban hydrology is the hydrology of urban areas or urban environment. This is how we define urban hydrology, which is important if we want to address urban hydrology related issues. The next one. Yeah, next one. So the next, so we have defined urban hydrology problem. The next one is, so what are the challenges now that we face in the area of urban hydrology? There are primarily two main challenges. First, enough water of adequate quality to all times and at an affordable cost. This is essentially what you define water security and sufficient resilience against weather extremes, against floods, against droughts. These are the two fundamental challenges. So the question is, have we as a global society met the challenge? From my perspective, the answer is emphatically no, we have not. And the next question is, can the challenge be met? The answer is yes, but with certain constraints. The next question is, are we on track to meet the challenge? The answer is partly yes and partly no. Next one. So let's now, in order to discuss a little more these issues that I have just enumerated, these questions that I have partly answered in the form of yes and no, I think it is important to take a look at the current global water situation. So first look at the water quantity. In 2020, 35% of world's population, meaning nearly 2.3 billion, was living in water-stressed countries. This is based on the United Nations Water Report published in 2021. By 2050, more than 50% of people will be water-stressed or water-scarce, which means nearly 6 billion people will be living under water-stressed or water-scarce conditions. On the other hand, water use will increase from 2,360 cubic kilometers in 1970 to 4,600 cubic kilometers in 2019. Over this period of time, over a period of nearly 29 years, you will see the water increase will be almost doubled. The demand for water would rise by 20 to 30% by 2050. The question then is the current water consumption sustainable? And then, of course, on the other hand, water quality. There is a dramatic degradation of quality, and this degradation is still continuing. So the overall situation is very alarming, to say the least. The next one. The next one, Prasad. Okay. So then, did you go back? Go back. Okay, now it's okay. Okay. No. Go forward. Forward. Go forward. Yeah, next one. Okay. So the question is, so what is currently happening now? The local water shortages are multiplying. Current patterns of use and abuse, that is the amount of water being withdrawn, is dangerously close to the limit and even beyond. An alarming number of rivers no longer reach the sea. And I'm not talking about small rivers, I'm talking about major rivers. For example, the Indus, the Rio Grande, the Colorado, the Murray-Darling, the Yellow River. These major rivers never basically see the sea. And these are main arteries of grain growing areas. Next, the question then is, we are still having severe and long droughts in Australia, in India, in Brazil, in South America, in the United States, and for that matter, all over the world. In many cases, hydroelectric power plants do not have enough water to drive the turbines, and there have been repeated and frequent brownouts. Next one. So again, to continue what is currently happening, excess pumping of water from rivers feeding the Aral Sea in Central Asia basically led to its collapse in 1980. Remember, the sea completely almost disappeared. The freshwater fish population are in precipitous decline. That means fish stocks have fallen by 30%, larger than fall in the populations of animals in any ecosystem. 50% of world's wetlands have drained or been damaged or have been destroyed in the 20th century. There has been a fall in the volume of fresh water in rivers. As a result, there has been an invasion of salt water in delta, changing the balance between fresh water and salt water. Excuse me. And of course, globally speaking, there has been a global water crisis, which is now significantly impacting the supply of food and other needed goods. So now the next one. So then the question is, so what are now the challenges? The challenges are population, water availability, water demand and use, water food energy nexus, water health nexus, water and energy nexus, climate change and water resources. And these challenges we will briefly go over. Okay, next one. Population, next one. Look at what is happening to the world population. Of course, here there are three estimates: low estimate, median estimate, and high estimate. So even if we go for low estimate, which is somewhat truly an underestimate, by 2050, the global population will be almost 10 billion, 9.4 billion. Median, 9.74 billion. High, 10.07 billion. By the end of the 21st century, that is the beginning of 22nd century, the global population will be almost 13 billion. And these population projections are within 95% confidence intervals. So they are pretty realistic. The question then will be that because of this massive increase in human population in the globe, there will be corresponding and attendant problems that cannot be escaped. It doesn't matter how well you do planning. And so the technical solutions only go to a certain extent, but they do not go far enough to address the real human problems. The next one. Now look at the other thing is the global population is shifting its demography. Now more than 50% of the global population lives in urban areas or peri-urban areas. And you can see the slide on the right side, this yellow slides, you will see the increase of nearly 2.18 billion in urban population, primarily in low income or middle income countries. Even in India, for example, now, there is a massive migration of people from rural areas to the urban area. And this, of course, is driven by a number of factors that I will briefly go over. But the purpose here is to show that there is a very rapid growth in urban population, primarily because of migration from rural areas to urban areas. The next one. And this is primarily seen, for example, look at in the middle part. The highest growth is in Eastern Asia, South Central Asia, Southern Asia, and then of course, Southeastern Asia. So that is where actually much of the growth in urban population is occurring. And then of course in Africa also, for example, in Eastern Africa and in Middle East, depending upon their population. So you can see that there is a very, very significant growth in urban population, and these figures are in terms of millions. The next one. Now let's look at the growth and urbanization trends in India. Now you can see here the rural population is on the decline and urban population is on the rise. And then of course, eventually in the next, eventually you will find that the urban population will be larger than the rural population even by 2080, 2050, unless we do something about it. And then of course, I will share with you my opinion as to what we should be doing. But let's, go to the next slide. Okay. The other situation is, look at again in India, look at the growth and urbanization, where the population is more than 10 million. Now remember, if you look at the European countries, figures, the total population of Sweden is less than 10 million. Norway, almost less than 5 million. And Switzerland, less than 10 million, actually less than 7, 8 million. Denmark, less than 5 million. If you look at, these 5 countries whose population is around 50 or 55 million, which include the UK, France, Germany, Italy, and then of course in Spain. But beyond that, almost all countries have population which is less than 10 million. So we are talking about the total population of the countries. Here we are talking about the population of the cities alone. And then of course there are a lot of cities where the population is between 5 to 4 cities, between 5 to 10 million, and this population continues to balloon. And of course this ballooning of population raises a number of issues. The next one. So the next challenge is how to make water available, water availability. Yeah, next, yeah, keep it here. Now look at here. This is the water availability scenario. Now, of course, we all know that the that nearly 97.5%, 97.8%, these are somewhat qualitative numbers, but not too different. The total water available is in the form of, basically in the form of seawater, the salt water, which is not usable. Only around 2.5, maximum, little less than 3% is available as fresh water. But then much of it is in the form of permanent snow and ice. So whatever little water is left, nearly 70% is in groundwater, in the form of groundwater. Out of that, half is below, available about a kilometer below the land surface, which is not extractable. Or if you want to extract it, it is just too expensive. It's just not possible. So that means we are talking about the water that is available within 1 kilometer of depth from the land surface. The amount of water that we quarrel is really that is available in the rivers, in the freshwater lakes, in the wetlands. It's a very small amount of water. And unfortunately, even that small amount of water is being contaminated so badly that it is not even directly usable. And so the question that I'm raising here is that to start with, we have only limited fresh water. Unless we do something about the seawater or do something about abatement of pollution or prevention of pollution, we just will not have enough fresh water to supply the needs of this growing population. Now, of course, look at the freshwater availability in cubic meters per second per year. This is based on the 2000 figure. Look at India. Where do we? We have already in the 1950s, let's say 55, India was a water surplus country. Today, it is a water stressed country. By United Nations definitions, in order to have to cross the water scarce category, we must have at least 1,700 cubic meters of water per person per year. We are actually, largely because of this dramatic increase in the population of the country, we are gradually shifting into what we have already entered into the water stressed mode. And eventually we will become a water scarce nation. Now this is without considering all other factors, assuming everything being normal. Even then, largely because of the rapid increase in population, plus the rapid increase in demand and misuse of, obviously, the management, we are already a water-stressed nation. The next one. So the next question is the water demand and use. So the next one. So where do we use the water? Obviously, we use water primarily for irrigation, for commercial purposes, domestic purposes, energy production, industrial production, mining activity, hydroelectric power generation, and livestock. These are basically the sectors where water is used and where there is demand for water. So the next one. Okay, now look at here. This is important. Irrigation in India uses, which means agriculture, uses approximately 80% or little more than 80% of the total freshwater supply. And livestock is a very small percentage, 3%. Even commercial use around 1%. Industries around 3%, mining around 1%, thermoelectric power generation about 3%, domestic about 7%. What this shows then is that if we can bring down agricultural irrigation consumption even by 10%, we can go a long way in making water available to a vast majority of people in the country without any difficulty. And that's where engineering comes into play. That's where hydrology comes into play. That's where electrical engineering comes into play. How can we make irrigation more efficient without compromising agricultural productivity? The next one. Okay, so let's look at the percentage water consumption in the world. Look at here. India uses 13% of the total freshwater supply in the world. China uses 12%. United States, even though the US population is only around less than 1/3 of India's population, but still it uses 9%. Russia 4%, Indonesia 4%, Nigeria 3%, Brazil 3%. The rest of the world uses 52%. So you see here that our water consumption is very, very high. Yeah, next one. Next one. Okay. Okay. So the annual water, now on the other hand, annual water withdrawal by sector. For example, look at North America. In North America, agriculture consumes only around 50% of the freshwater supply. And 37% is used up by 13% for domestic consumption. And of course, 37% is agriculture, and 50% is for industry in North America as a whole. In Europe, look at industry, 57%. Agriculture, only 21%. Domestic, 22%. But look at Asia. In much of the water, 81% is used up by agriculture. Industry, and 9% domestic. So it's only 10% is used by industry. And so I think this gives a pretty good idea where we can make a difference by employing latest technical know-how, latest technologies. And I'm not talking about technologies simply developed in civil engineering or agriculture engineering. And I will be speaking a little later about this issue, the next one. Okay, now let's look at the individual use. Individual use, normally a person needs for survival 4 to 5 gallons of water per day. An average American uses at home per day 100 to 175 gallons. Of course, their gallon is around 3.8 liters per gallon, not 5 liters. An average African family uses only around 5 gallons. Now, Middle Eastern and North African countries, they call MENA. They are in absolute water scarcity situation because their water supply is less than 500 cubic meters per person. Actually, their water supply is per day. It's just unbelievable. Kuwait has the least per capita water availability, which is 27 cubic meters in 1970, 9 cubic meters in 2001, and it projected to decrease to 5 cubic meters per person per year by 2025. Yet, Kuwait has the highest per capita water consumption in the world. 200 liters per person per day in the 1960s, currently 500 liters per person per day. It's just unbelievable. The next one. So the demography. Increasing water demand follows population growth, economic development, and changing consumption patterns. Water use has increased by 600% over the past 100 years. Population is likely to rise by another 1.7 to 2.5 billion or 20 to 34% by 2050. So the demand for water will rise by 20 to 30% by 2050, roughly 900 to 1400 cubic kilometers of water per year. And this estimation may be pretty optimistic. Not just the absolute number, but the habits and the diets that make the biggest difference. And this I will illustrate. Food demand in 2050 will increase by 60%. If there is no change in agricultural efficiency, the world will need more, as much as 60% more water for agriculture to feed the extra 2 billion mouths. This is roughly 1500 cubic meter of water, as much as is used for all purposes in the world outside of Asia. Where are we going to get this water from? The next one. And this shows the water use in India. Water use per cubic kilometers per year. In 2020, you look at, it is almost, even if you look at the forecast one, it's almost 550, 2.5 times it has increased. And these are of course, these numbers are given by different agencies, so there are a little bit of differences in the figures, but overall, the trend is pretty much the same. So the next one. Okay, so the question then is, what are the factors that are affecting the water use? Urbanization, because the increasing number of people will dwell in cities and they use more water. For the population centers, there are water intensive social development, deforestation, declining groundwater tables, and then of course intensified flow of high volume or low quality stormwater runoff to rivers and streams, disturbed natural environment, pipelines, roads, wastewater discharge network. All these things actually are occurring because of urbanization. And the farmers use about 3/4 of the world's water, industry less than 20%, domestic and municipal use accounts for nearly 10%. And then of course the climate change. So these are the factors which are affecting the water use. Yeah, the next one. Next one. So the next question is water, food, and energy nexus. Well, look at the water requirement or water use. Virtual water embedded in food products. Roughly 1,000 liters of water is needed to grow 1 kg of grain. On the other end, 15,500 liters of water is needed to grow 1 kg of beef. You see the difference? More than 15.5 times. Meaty American and European diets consume 5,000 liters of water per day. Vegetarian, African, and Asian diets, on the other hand, consume only 2,000 liters of water per day. Meat consumption in China in 1985 was 20 kg per year per head. It increased to 50 kg per year per head in 2009. Now, if you compute the total water used in growing that much of meat, then it will be equivalent to 390 cubic kilometers, which is the total water used in entire European countries, which means the shift in dietary habits is almost impossible to reverse. But the dietary habits make a huge difference in the water consumption. And on the right side, you see the figures which shows how much water is needed to grow maize, soybean, wheat, rice. And of course, look at the lower side, which is very interesting. 1 kg of coffee requires 20,000 liters of water. 1/4 pound of hamburger requires 11,000 liters of water. 1 cotton t-shirt, 7,000 liters of water. 1 kg of cheese, 5,000 liters of water. 1 kg of sugar, 3,000 liters of water. 1 kg of milk, 2,000 liters of water. 1,001 kg of wheat, 1,000 liters of water. Now you can see why our forebears emphasized the vegetarian diets. You can see, even though those days there was no dearth of water, but this clearly shows where and how much water is needed. The next one, and I'll give you some more. And let's look at the water health nexus. Next one. So access to clean water and sanitation and hygiene. Globally, more than 785 million people do not have access to basic water service, and more than 885 million people do not have safe water to drink. More than 25% of the world's population, which means nearly 2 billion, do not have access to basic sanitation facility. More than 35% of the world's population, which is 3 billion, lack adequate facilities to safely wash their hands at home. 1,400 children under 5 die every day from diarrhea, mostly in developing countries, which is 9% of the 5.8 million annually deaths of children under age 5. 1.7 billion cases of childhood diarrhea every year occur. 3 million cholera cases and 95,000 cholera deaths occur annually every year, largely because of lack of sanitation, hygiene, and lack of clean water. Next one. So the most effective management intervention when it comes to safeguarding human health is water sanitation, hygiene, has the potential to prevent at least 9% of the global disease burden and 6% of global deaths. Water and sanitation interventions are cost effective across the entire world. Improved sanitation contributed to a 15% decrease in diarrheal deaths in Southeast Asia, East Asia, and Oceania, and more than 10% decrease in diarrheal deaths globally. This is the impact of safe drinking water. Next one. Let's look at water and energy. And this is quite interesting. Of course, huge amounts of energy are needed for making water available to various users. For example, energy is used for withdrawal, for conveyance, for treatment, and for supply. In USA, 116 billion pounds of carbon dioxide, while producing such energy, basically is generated, which is equal to pollution from 10 million cars. So the energy that we use, that we generate, comes with a lot of baggage. Now, the other areas where energy is needed is source and conveyance, drinking water treatment, distribution, end use, wastewater treatment. In all of these areas, energy is needed. The next one. And this is really interesting. Electricity production is one of the largest users of water. For example, for a 60-watt incandescent light bulb burning for 12 hours a day for a year in 111 million houses, a power plant will consume about 655 billion gallons of water. That means water use efficiency. Look at here. Or what in let's write, this is really important. How many gallons of water are needed to produce 1 million BTU? Natural gas, 3 gallons. Hydroelectric power, 20 gallons. Fossil fuel, thermoelectric, 230 to 270 gallons. Coal, 41 to 464 gallons. Nuclear, 2,400 to 5,600 gallons. Ethanol, 2,500 to 20,100 gallons of water will be needed. Biodiesel, 14,000 to 75,000 gallons of water will be needed. So we talk about green energy, ethanol production, biodiesel production. Look at, so this is an irony when it comes to biofuels, because currently 2% of irrigated water is used for energy crops in the United States. If all plans were implemented, 180 cubic kilometers of water will be needed. We don't have that much of water. But look at here, biodiesel requires 14,000 to 75,000 gallons of water to produce 1 million BTU, where a natural gas needs only 3. Hydroelectric needs only 20 gallons. But in case of hydroelectric, you can use the same water. Well, this is so people often do not quite realize that there is a lot of water that is consumed for producing energy, which we don't really see. It's just like out of sight, out of mind. Next one. So the next challenge is climate change and water resources. The next one. Now, of course, so here you will see that in recent years, of course, this is on the scale from 0 to year 2000, when we did not really have measurements. So these measurements are pretty much constructed based on paleo records and so on. But look at the recent years when we have, in the recent year, this is the temperature anomaly on the right side, that there is a sharp increase in the temperature, particularly during the last 50s, 60s, 70 years, especially in the last 30, 40 years. The next one, largely because of we call climate change. And look at, likewise, annual and seasonal temperature trends in India. The trend is toward increase in the temperature. Pre-monsoon as well as post-monsoon, 0.2 degrees, in pre-monsoon 0.5 degrees, and post-monsoon again 0.5 degrees, all over. You can see this slide essentially shows annual increases, increase in the winter, pre-monsoon, monsoon, and post-monsoon. Everywhere you see the increase. The next one. So the question is, so how does climate change impact water resources? It impacts through the intensification of hydrologic cycle, which is manifested by increased frequency of floods and droughts, increased variability of rainfall, shortening of snowfall season, advanced start of spring snowmelt, accelerated glacial melting, changes in temperature regime, which means evapotranspiration regime, changes in freshwater availability, changes in water consumption, changes in food production, changes in viral and bacterial activity. This is how actually the climate change, and this list is not exhaustive by any means. This is just a simple illustration of what the impact of climate change is in terms of hydrology. Now, of course, you can see here, these are the occurrence of drought frequencies. I think it's not complete showing, but the droughts from 1996 to 2015, there have been number of occurrences have been 10. Also, it's also increased the frequency and the magnitude of extreme weather. People also annually affected by droughts, and the number of people affected, which is almost 10 billion, 1.1 billion people actually were affected. 22,000 or actually more people were actually killed during this period from 1996 to 2015, during a period of 2 decades, approximately 2 decades. And the damage is more than $100 billion during this period. So look at the impact of changing climate simply on one weather extreme, which is drought. The next one. I think the whole slide is not showing up, but in any event, likewise, if we look at the other extreme, which is the flood extreme, we have a number of occurrences during this 20-year period, 100 floods we have incurred. Likewise, flood events have increased from an annual average of 127, okay, in 1995 to 171. Now, the previous one, okay, yeah, stay there. So the people at risk from floods is actually projected to increase from 1.2 billion in 2010 to approximately 1.6 billion in 2050. So in other words, nearly 20% of the world population, and the economic loss is expected to be around US 1.4 trillion by 2050. Just unbelievable figure. This figure is more than the annual GNP of most countries if you take the US, China, and Germany aside. So the people annually affected by flooding is almost 35 million. The next one. Okay, so this is actually, this also shows, this slide shows the impact of climate change on precipitation, evaporation, and available water. And actually these are essentially these graphs on the left side are showing changes in evaporation, that evaporation increasing, precipitation, and availability of water. The next one. So the potential change in total production of maize, soybean, wheat, and rice in total calories at the end of the century, given the maximum use of available water. Look at here. The increase is more than 10% in these gray area, these lightly shaded green areas, and the decrease is 0 to 20% down. But look at India. For example, much India, especially in the northern part of India, you will see a much greater impact. The next one. And of course, this shows the projected number of hot days, more than 30 degrees Celsius. It is rising at a significant rate. Likewise, the projected number of heavy rainy days means any day when the rainfall or precipitation is more than 100 millimeters. This is also increasing rapidly. The next one. And the other part is, which is even more important, which is the changing rainfall patterns. The increase in extreme rains in Northwest during summer monsoon, lower number of rainy days along East Coast, a record 900 millimeter of rainfall, say for example, Mumbai on July 26 and 27, 2005, loss of over nearly 1,000 lives and more than $250 million US. This is what is happening when the rainfall patterns are changing, because these changes have a direct impact on agricultural productivity. The next one. And look at the floods, particularly if we look at the floods in India. Flood events in 2000 to 2017, Bangladesh, India, Myanmar, and Nepal. And here you will see the very rapid increase in the floods, almost all over the country, barring a few areas, for example, in some parts of Southern Peninsula, and of course, some parts of the Maharashtra, and of course, some parts of extreme north, Jammu and Kashmir. Otherwise, you see a rapid rise. Next one. So, in terms of drought, 50% of droughts associated with El Nino. Consecutive droughts in 1990 and 2000 in Pakistan and Northwest India led to sharp decline in water table. Consecutive droughts between 2000 and 2002 caused crop failures, mass starvation, and affected 11 million people in Orissa. droughts in Northeast Asia during summer monsoon in 2006. The cyclones increase in the frequency of extreme cyclonic storms over North Indian Ocean near the Arabian Sea. So these are the direct impacts. Next one. And of course, these are the weather-related disasters in India during the period of 1980 to 2006. And you see there's a rapid rise, especially the extreme temperatures. These are the yellow lines. And of course, the green line are the green lines depict the extreme weather storms, and the blue lines extreme floods. The next one. And of course, then the monsoon patterns are also changing, which are monsoons in India are essentially the important source of water. And there is an uneven distribution of rainfall, 20% rise in all summer monsoon rainfall. Climate change will make monsoon even more unpredictable, which then will accentuate extreme, particularly severe droughts and severe flooding. And El Nino can delay or cause the monsoon to fail. And so the climate change then may impact the duration and intensity of El Nino and thus the entire monsoon pattern. And this is what is happening. The next one. So the monsoon, the climate change will also directly impact groundwater, or the influences of climate on groundwater is directly felt through the replenishment by recharge, indirectly through changes in groundwater use. And studies have shown that overpumping due to growing demand has a more severe impact than has the climate, and which is what is happening throughout the country. The next one. The climate change is also, just hold here, look at here. The 7 largest groundwater pumping countries are India tops, way high. Then of course the USA, China, and Pakistan, Iran, and Mexico, and Saudi Arabia. But there is no comparison. Actually, the second is the US, but India is way high. And this is what is causing this rapid, this is being manifested by rapid decline in groundwater table. The next one. Yeah. And this is just an example of Madras aquifer, and which essentially pretty much shows the same thing. The next one. So the impacts on megacities. Of course, the megacities are expanding. There's a rapid rate of urbanization because of migration to the cities. Many megacities are on the coastline. So where is the needed water going to come from? And what is happening to the coastal zone flooding? The next one. I think that will show. The next, yeah, okay. So the next question is the global scale extreme sea level rise by 2021. And this is going to have a severe impact on the cities which are situated along the coastline, say for example Mumbai or Madras, and which are not too far. For example, even Bhubaneswar, it is not too far from the coastline. Certainly, Jagdishpur is almost on the coastline, and there are other cities. Calcutta is really not that far. And all these cities will be severely impacted because this slide shows essentially the global distribution of projected 100-year return period extreme sea level. So an increase of 40% of the world area will be impacted by the sea level rise. 52% of the population obviously will be impacted, will be at risk by the year 2021. So the projected global coastal area flooding is 68% due to tide and storm event, and 32% due to regional sea level rise. This is going to have very severe consequences, largely because of sea level rise, which is triggered by climate change. And so the people affected by rising sea levels by 2021 assuming a rise of only about 0.5 to 0.7 meter. So this will be, so the people, lives in the global land below annual flood level will increase from 110 million in 2010 to 190 million by 2019 under low carbon. And it is estimated to 630 million, that is under sea level, that is under low carbon level. Yeah, the next one. Yeah. Now look at here, the base here. So this is the loss of water bodies due to urbanization. And then of course the number of major flood events in 2001. This actually tells you, I don't need to go over the number of flood events that have occurred over different areas, but you can see here that there is a tremendous loss of water bodies due to urbanization. And this is what is happening. For example, even in Bangalore or in Udaipur, they used to have hundreds of lakes. Now the number of lakes has decreased by more than 50%. The next one. So the last one is, so what are the opportunities then for those who would like to pursue their career in urban hydrology? The next one. The next one. Yeah, the first one is water supply. The next one. Prasad, the next one. Okay. So in order to ensure water security, there are two pieces of the puzzle, supply and the demand. So we have to manage supply, which means supply management. And then of course we have to manage demand. So that means demand management. The demand management includes the use management, storage management, and then of course the demand management itself, the next one. So in order to have sustainable water supply and sustainable use, there is no one solution actually that fits all. We will have to have an integrated solution, which will entail conservation, efficient use, treatment, recycling, reuse, and development of additional resources. We want to have sustainable water supply. This is the only way. There is no other way out. The next one. So we have to have integrated. That means that will require integrated water resources management with simultaneous consideration of reduction in water consumption, recycling of water, use of water, conservation of water, use of water efficiently or efficient use of water, and then of course proper management. The next one. The next one. So how does then hydrology fit into all this? Basically, urban hydrology addresses two types of problems, design problems and non-design problems. Design problems include design of water supply schemes, design of drainage infrastructure, design of highway pavements, culverts and bridges, urban zoning or demarcation of urban zoning, design of parking lots, design of airport runways. All these things cannot be done without invoking urban hydrologic principles and theories. But there are also non-design problems whose solution depends on urban hydrology. For example, pollution abatement, ecological sustainability, health impact, to reduce adverse health impact, and of course to mitigate climate change impact. And that means the management of the entire waterside system and the ecosystem. The next one. So in order to accomplish those two types of problems, we need hydrologic data. Without data, you cannot really do anything. There is no engineering, no science can be done. So the data include hydrometeorologic, topologic, geomorphologic, hydrologic, land use, lithologic, and hydraulic. So how do we acquire these data? using remote sensing technology, satellite technology, radar technology, digital terrain and elevation model, chemical traces. These are the methods that we have. So once we acquire the data that we need, then how do we process and manage it? Now, to do that, we have geographical information systems, we have database management systems. So the next one, which we need to employ, which most people are doing it. So the other question is, in order to do the design problems or to address non-design problems, precipitation, there is precipitation variability in terms of the storm movement, spatial variability, temporal variability, rainfall, field description, and of course, rainfall forecasting. Next one, which we need to address. And then of course, the next one is we have to take into consideration the variability in watershed characteristics, because in urban areas, you see the characteristics of urban areas are not homogeneous and isotropic by any stretch of imagination. So there is spatiability, for example, of hydraulic roughness, which directly impacts runoff dynamics and hydrograph, formation of shocks, and there is spatial variability in infiltration because there is spatial variability in hydraulic conductivity, steady infiltration, mean infiltration, that impact runoff dynamics and runoff hydrograph. The next one. Then there are scaling issues because the spatial heterogeneity in watershed characteristics is there. And of course, there is spatial variability in water-related processes. But of course, there is a physical spatial size. For example, if we want to do the modeling, then we may have to use representative elementary area or hydrologic response units or computational grid size. Now, these spatial units somewhat are different from those that are used in routine rural hydrologic problems. Then, of course, there are scaling issues. So there is time interval of observation, computational grid size, and temporal variability of processes. If we want to do urban hydrology, then of course we have to take into consideration spatial scaling, physical spatial size, and temporal scaling. The next one. So once we want to either use a model or develop a model, then of course the issues are related to parameter estimation algorithm, which require specification of an objective function, optimization algorithm, determination criterion, and calibration data. Then we have to also handle data errors. And of course, we have to determine data needs, both quantity and information richness wise. Yeah. And also, we have to represent uncertainty of the calibrated model. And of course, these days, we are also using artificial neural networks. But the most important part is not just urban hydrology by itself is not sufficient. The urban hydrologic models or urban hydrology has to be coupled with geochemistry, environmental biology, environmental chemistry, earth science, meteorology, oceanography, especially if the urban area is located along the seacoast, and then of course, most importantly, social sciences, economics, and decision making. So any urban hydrologic exercise, modeling exercise will have to be integrated with these other branches. The next one. So what are then the tools that are available for doing urban hydrologic modeling or addressing urban hydrologic problems? Water sources systems analysis or decision making. We do have mechanistic tools, we have data mining tools, we have uncertainty analysis, we have information theories such as entropy theory, we have risk analysis, multivariate stochastic analysis such as Kapula theory, we have artificial intelligence systems, optimization algorithms, we have decision support systems, we have GIS, geographical information systems, and data collection and mining. So we do have actually the tools that we need to do urban hydrology. And then, of course, urban hydrology. The challenges are that in urban hydrology, we need more data at finer spatial resolutions, unfortunately, which we do not have. And of course, for regional scale models, for uncertainty analysis, long-term forecasting ahead of time, and for example, probable maximum precipitation, probable maximum flood. For all this, we need the data, but we are not doing all this. And then, of course, we have to do integration with biogeochemical models, integration with climate models, as well as with ecosystem models, climate change and global warming, and coupling for decision-making issues, for example, social, political, economic, environmental. And let me emphasize here, these issues sometimes tend to be far more important than the technology-related issues that we have been discussing. It is the social, it is the political, it is the economic, it is the environmental, it is the policy-making issues that take on far greater significance than the technical issues. So the challenges that we have are that we have to have user-friendly modeling tools. We have to have model choices, and each choice should be associated with model credibility, quantitative credibility, which means we have to scope out urban hydrology. So the question then arises, where do we go from here? The next one. Okay. We go from here, there will be, and there is increasing societal demand for models. But there is increasing emphasis on linking these models to environmental and ecosystems models. The emphasis should be on user friendliness. We must incorporate information technology, computer-based design, artificial intelligence, and space technology. And we must specify model uncertainty and reliability. And we must also clearly state model competitiveness. Only then we will be able to select the right kind of model for addressing a given urban hydrologic problem. The next one. Okay, so let's reflect and re-examine. We have water, energy, food security system. If we want to ensure water, food, energy security, there must be a strong partnership among academia, government sector, NGOs, and private sector. In the education system, we have to have a re-examination where now, because the technology is changing, our demands are changing, our problems are changing, we have to train the trainers. And also we have to teach the teachers. And this is important, and this should be a continuing exercise. So the next one. So this takes us to where are we actually headed as a society. First, we define what exactly do we mean by development. And what should be our development paradigm? Should it be concentrated versus distributed, which is what is happening these days? For example, everybody wants to come to a city, but nobody really raises the question, why do people want to move to a city? This is very simple, because that is where the development is. That is where the opportunities are. Opportunities in terms of education facilities, health facilities, transportation facilities, employment facilities, and what have you. But is that the way to develop a nation? Why don't we have the distributed development? Why should all the facilities be concentrated only in a given number of areas? Look at, for example, our country, India. 70% of the people live in rural areas. But 90% of the development, I would say 95% of the development occurs only only in the cities. And in the cities also, if you really look at it, I would say only where about 10 to 15% of the people live. So that means you are developing 15% of people at the cost of the remaining 85% of the people. Is that the way to develop? I think this is a question that all of us need to reflect on. Second, what should be the development scales? Individual to community, to society, to nation. I think we need to focus on this development scale. What should our scale be for developing? Do we want to develop every family or every community or only big cities? Or how do we define national development? Why development only for privileged few? Why not for everybody? The next is basically the development to management. There has to be a paradigm shift from development to management when it comes to managing urban hydrologic problems. Now, of course, we have made huge scientific and technological progress. The question is, have we made an equal level of progress in the social arena, particularly in terms of our value system? I'm not so sure about it. We are witnessing massive changes in global demographic landscape. Are we able to cope with it? Should we allow this change in the demographic landscape to continue? Now, of course, that takes us to our human nature. Now, we see conflicts and wars, we see competition, we see convergence and divergence of views. But ultimately, the point I'm trying to make is we have to integrate engineering, technology, socio-economic, political science, human values, and of course, our entire way of thinking as a society, as human beings. And we should go back and redefine what we want to accomplish in life. Life of a nation, or life of a society, or for that matter, as a civilization. The next one, I think this is, so what should be our way forward then? We have to have a thinking outside the box. We should be innovative, revolutionary, and self-sustaining. Then, of course, we have to have diverse and multi-institutional partnership. We have to price and value water for enhancing water use and efficiency. There must be a strong integrated planning for water, energy, and agriculture. And there must be a robust regional capacity building. And of course, development paradigm, distributed versus controlled urban growth. This is the only way we can move forward. So to summarize, I think it is time for us to sit back and take a stock of the current situation, recognize our social and cultural constraints, and take account of looming global changes, re-examine, revalue, or re-evaluate our social values and our value systems. If we do that, then our future can be bright or dark. It's all in our hands. So with that, I would thank once again Jyothi, and I would say, let me say that natural resources are God's gift. We must use them wisely. We owe it to our future generations that we leave them in a better shape than the shape we got them in. So with that, I want to take the opportunity to thank Hari Prasad and Jyothi for inviting me to speak at the inauguration of your 5-day workshop. And I want to wish the workshop participants all success, and I wish you luck in having the workshop run smoothly for the next 5 days. And it's a pleasure meeting once again Dean Ashok, and of course my colleagues Professor Gajendra Singh and Professor Vasant Maheshwari, and of course good luck to all the workshop participants. Thank you. If there are any questions, I will be happy to answer. For Professor Gajendra Singh, it's almost 2 o'clock in the night.
Thank you, sir. Thank you. Thank you. I think very interesting lecture and many areas which you have thrown to the researchers, and they can select their topics generally. Researchers are always in the way what topic to be chosen and all, but you have given them many options, and they should think which topic they can able to carry out and all. So I think if there is any question, they can put in the chat box, and that can be later on also addressed. So my sincere vote of thanks to our Professor Vijay P. Singh sir, and for your valuable time, precious time, and to our Dr. Gajendra Singh sir and Dr. Prasad Maheshwari for giving their valuable time. Thank you very much, sir. And even the midnight now, and still you are giving your valuable time. And extend my hearty thanks to the experts who has attended, Dr. Sharad Chaim and Engineer Jagdish from ISRO, Asha Kiran, and Dr. Munavalli and Dr. Shubha, who has joined this program. And even our Dr. Mujumdar is also there. He is also for the next session. Welcome you also, sir. And my thanks to Dean College of Technology, Dr. Lakmanda Ashok, and also our head of the department, P.S. Mahar, for their valuable support. And my sincere thanks to all the participants who has joined early, because 8:30 only they are also joined. So my sincere thanks to them, and extending my valuable thanks to in charge CCF for networking facility, and even for NAHEP University Center of our university, and Western Sydney University for their valuable support, and even for the AICTE, which has given the fund for organizing this program. Once again, thank you all. Once again, thank you and namaskar for support. I think we have some 10 minutes break, virtual tea break. Prasad, Dr. Prasad.
Yeah, thanks to all. We are slightly, the schedule has been delayed. So with permission from Professor Pradeep Majumdar sir from IISc Bangalore, he has already joined. Sir, let me have some just 10 minutes break, sir.
Virtual tea break.
Yeah.
Yes, absolutely. Yeah. So, Professor Singh, it was a privilege to listen to you. Thank you so much. Professor Prasad, please go ahead and have a break. I'll join at whatever time you want.
Just after
Thank you, Pradeep. It's a pleasure seeing you again.
Thank you, Professor Singh.
Namaste.
Gajendra Singh sir, namaste. Vijay Singh sir, namaste.
I'd like to say good night. I think it's quite late for me, so
Thank
thank you.
2 o'clock.
Thank you very much, sir. Thank you.